I'm Dimitris from the University of Cambridge, and this is our work on sequence multitask models to forecast mood, to be presented at KDD 2019. A commonly overlooked area in data science is mental health, which affects roughly 1 in 4 in the UK, while traditional monitoring, which is based on surveys and controlled experiments, cannot scale. On the other hand, current smartphones come equipped with sensors and push notifications which allow to keep track of users' mood throughout the day. When we deal with this kind of data though, noise and sparsity are the main challenges. Addressing them is crucial in order to provide effective feedback. Our work proposes an encoder-decoder neural network to forecast future mood based solely on previous mood sequences, with a sliding window setup. The proposed model consists of 3 parts: a long, short-term memory encoder that processes the mood sequence, a copy vector that repeats the encoder 2D output as many times as the output length, and another LSTM that predicts future mood sequences. 2 fully connected layers are applied to every time step of the output, since we measure mood on a bidimensional scale, thus enabling multitask training. We use data from the EmotionSense app, which collect the data from passive sensors and short experience sampling twice per day using this visual affect grid or sliders. For the purposes of this work, we use only the 2-dimensional affect grid data. Most of the users report around neutral and calm and happy areas. Also, we observe some retention issues that add to the challenge of the sparsity. Mood reporting, when seen at the daily or weekly level, tends to be predictable for some users and a bit more challenging for others. Therefore, we need models that can learn the intra-individual variability. Our results show that 3 weeks is the best window of mood reporting, while our models outperform machine learning regressors and simple baselines. Multitask learning seems to help the prediction of the arousal. Model interpretability is always important in clinical setups. Therefore, we analyze the role of the layers in forecasting mood. To do so, we apply PCA to the test set before training, the activations of the encoder, and the activations of the decoder after training. As we move into deeper layers, the network lays out the continuum of positive and negative mood, even though it has been trained to solely predict the next week's mood. Finally, we inspect how the individual neurons of the decoder layer fire as we pass the test set. Some neurons fire almost always with the same slope, while others are more conservative with almost flat lines. This helps us identify important neurons. You can find more results and post-hoc analysis in our paper. We believe this work provides psychologists and developers of mobile mental health applications with a ready-to-use and effective tool for early diagnosis of mental health issues at scale.